Okay, so which one is better? Again, just final question. Virtual circuits or datagram switching? Yeah, give me one reason why datagram is better. Think of another reason why the other one is better. Yeah. For large packets, virtual circuit is better. Where did you hear that? Large amount of data, maybe. Yeah, but not large packets. Like if we have a huge data to send, the virtual circuit is better. Why? It's faster than datagram. It's a bad answer. Why is it better? You're right, it's better, but not the reason. Why is virtual circuit better to use if we need to transfer a lot of data?
We can reach.
Because it can guarantee the quality of service, not because it's faster. Right? Okay. Give me one reason why datagram is better.
It's more faster, maybe.
It's faster.
Yeah.
Enough packet size. Datagram is not fast.
Yeah.
Let's say they have the same speed. When we say faster, if you mean the delivery, how fast we can transfer bits, they both have the same transmitters. How come it can be faster? Or is it really faster?
Because it doesn't need any call setup.
Because it doesn't need call setup. It doesn't necessarily mean it's. When is datagram can be faster than virtual circuit?
When it comes to
No.
sending out the packets.
Thank you. Any idea why is there? When is datagram faster?
For sending small packets.
For sending small data, not packets, guys. You're making the same mistake as you. There's a difference between the data we want to send and the packets we want to split them into. Don't say small packets or large packets now. We're talking about huge data or small data. So if the message is short, very small message you want to send, in datagram you just send it. In virtual circuit, you send first a request and wait for the response and then send it. By the time you sent it, the datagram had already sent it. In the case of large data sets, they both have the same speed, but sometimes the datagram slows down. It cannot always be fast. So it does not guarantee the quality of service. Virtual circuits will guarantee the quality of service. Do you agree with that? Good. Why? How come virtual circuits can guarantee a quality of service? Any idea? A datagram cannot guarantee it. Now we know we're talking about quality of service. Datagram cannot guarantee always the quality of service is great, but virtual circuit can guarantee it. Why? Virtual circuit can block new users. It can limit the number of users in the network. Datagram cannot limit the number of users or it cannot block users. Okay, enough about switching. What are the problems with parity error detection system? Give me one problem with it. There are 2 bits change. A very specific answer. Can you give me a better general answer? No, okay, thank you for that's a good answer, but let me stick to the errors it cannot discover. What errors parity system has a problem with it cannot discover? 2 bits in the same byte. That's exactly what he said. That's not a good answer. You won't get full mark for that answer. Yeah, what do you think? Anybody?
I was going to say something.
Any even number of bits in the same frame or packet, right? Wrong answer. That's what she said. In what? In one byte. In one byte. An even number of bits in one byte. Not one bit there and one bit. If they have to be in the same byte, 2 or 6 or 8. So it's an even number of errors or bits that flip in the same byte. Don't forget the same byte. The problem with parity bit error detection system. If one bit flips, we'll discover it. In the same byte, if 2 flips, we won't discover it. Because it just counts how many bits are there that have the value 1, even or odd, for example. If 2 bits flip, they will not change. We would not discover them. 4 bits, we would not discover them. So it's not just 2, even number, okay? In the same byte, don't forget the same byte. Parity error detection system. It has a lot of or little redundant data. How much redundant data does parity systems have or generate? Like when you send the user data, how much extra data do you send with it generated by the error system? One bit in every byte. Okay. How about 7 kilobytes? How much redundant data do you send with 7 kilobytes? How about 7 million bytes? If your data is 7 million bytes, how much redundant data do you expect to send with it?
21.
It's 7 bits. 1 bit is extra weight. Right? If you send 7 million, how much extra weight you will be sending? 1 million. So it's a ratio of 1 to 7. This is the idea. Or 1 in 8. So it's a ratio, probably works easier. So say if you're sending, I don't know, 7 billion, you'll be sending 1 billion of extra weight. And that's a lot of redundant data, as we will discover in other systems.
Talk about bytes and bits, right?
Yeah.
So could you please clarify that when it comes to bytes, what should we expect in the redundancy?
The total amount of data, it doesn't matter, even if it's in kilo or million bytes or bits, or if you only send 14 bits, you'll be sending 2 bits extra. It's a ratio of 1 to 7. If you send 14 million, you'll be sending million. All these, what we send is 1 bit every byte, but it can accumulate. If there are lots of bytes, then they're going to have redundant data, a lot of parity. So you can say it in bits or in bytes, or, it doesn't matter, it's a ratio. If you send a very small frame, there'd be little redundant data, but very large frames or packet, it'll be more. On a day, billions and billions of bytes, and 1/7 of those, or 1/8 of those, is going to be redundancy. So it's very expensive. All right, so we looked at parity system and we looked at block parity system. What's better, if you remember from last week, the parity or the block parity? Any idea? The block parity, why?
Horizontally and vertically.
Because it can discover more errors, basically. Those 2 bits that happen in 1 byte, it will discover them if we do the counting vertically. The block, it's like a matrix, it counts the rows and the columns. In the original parity system, we only count the rows. So if we get 2 bits in the same row, we don't discover it. But with the block parity, we don't discover it, but we discover it if we count vertically. So it will discover more errors at very little extra cost. But never mind that. Let's go down to CRC. It's probably the most successful system so far in computer communication. It's the most successful error detection system. Let's look at it first briefly. It's a binary system, but let's look at the ordinary decimal system just to put the idea across. let's say you're sending data, whatever the data is, numbers or, let's look at them as numbers now. And imagine you sent few numbers, say 5, 7, that's 12, and 8 is 20, and for example, 13. So these numbers 20, 28, 33. So the total is 33 altogether. So the data we are sending adds up to a number 33. In CRC, the sender and the receiver agree on a number, or agree on a key. We use a key. The generator, the one that generates the code that goes at the end of the frame. And the key is just a divisor, a number that we use it to divide. For example, let's say the key is 5, just for argument's sake. So what the sender does, divides the entire data, that's 33 divided by 5. What's 33 divided by 5? 6, and the remainder is 3. It says the system, this is how a system works. What will it take? What complement will this number have, or this number 33 have, in order for it to divide by 5 without any remainder? Well, we have 33. What would complement the 3 in order so it becomes 5, so it will divide by 5 without any remainder? So in this case, 2, right? If this number was 33 plus 2, which is 35. If it was 35, it would have divided by 5, which is 7. 7 times 5 is 35, remainder 0. So that's the number we want. That's the magic number we want, and we put it there. We send it with the data. In such a way, the receiver, this is now what the receiver does. Receives this. This is the original user data. And this is the extra number sent by the sender. We call it the CRC. That's used to check the correct frame. So what the sender does, adds all these numbers, for example. And what's the total there? 5 plus 7 plus 8, 13 plus 2, 35. Regenerator, which is 35 divided by 5 is 7, 7 times 5, 35, remainder 0. It says, I am assuming everything is good. If it wasn't 0, I'd expect an error. If, for example, during transmission, this 8 turned into 9, for example, that's an error. Now we'd get 36 by 5, it kind of is 7, 7 times 5, 35, remainder 1. Oh, the remainder is not 0, then say there is an error somewhere. So that's the idea of CRC. It looks like it a lot of division, which is, remember, it's going to make it slow, but it doesn't divide. It actually performs another logical operation that simulates division, and it's called XORing. Everybody knows what an XOR? Everybody knows the OR and operations? Yeah? Do you remember the logical and OR? Like you have two switches. I say if you switch A and switch B, the light will go on. So both switches must be on, one. If one of them is 0, the light doesn't come on. That's an AND. OR is either one of them will switch the light on. XOR is called exclusive OR. Just to remind you. Okay, so this is the basic idea, but we do it in binary. In binary, we don't do division, we do XORing. So it's all CRC is, in fact, logical operation. It's extremely fast from a speed point of view. Now let me just show you what XOR table looks like. I'm sure you know the OR. For example, if you have two switches, here's the two switches, A and B, and now here's a bulb and a battery. This is an OR operation. So current doesn't go anywhere if the two switches are open, the light is off. But if we close switch A or switch B, the light will go. If we close both of them, the light will be on as well. This is called the OR table. XOR is similar to the OR, but X stands for exclusive, only one of them. You can't use the two of them. So if we switch A, close it, the light will come on. We open it, the light go off. We close B, the light will come on. Exclusive, you see, don't close the two of them. The light will not work. So that's X, that's what X means, exclusive. So an XOR is something like this. If you have two switches, A and B, exclusive OR, what's the result? So if both switches are open, the result, or the lamp, the bulb, will be off. If switch B is on and switch A is off, if the result is 1, and if A is 1 and B is 0, the light is on. But if both of them are on, it's still 0. That's the exclusive. That's how division operation is actually done in computers. And this is how CRC actually works. So you need to remember this. And in fact, I find it difficult to remember when you're in a hurry. The easy way to remember it for me is say, okay, if A and B are 0, both zeros, both off, the result is 0. If they are both on, the result is also 0. So if they are similar, the result is always 0. If they are different, the result is 1. As long as you know the outcome. But that's my special or easy way of remembering what's the result of XOR. Well, if the two switches are similar, then the result is off. Nothing comes out. Let's go back to CRC. Now, those two pieces of information we need. And how does CRC work? And you need to know how it works. You need to actually do the operation. This is almost an exam question. A guaranteed exam question. There's always a question on CRC, and there's always calculations. And this is one of the calculations you need to be familiar with. Right. Take some data, and this is exactly how it actually happens on the computer. So let's take some data. Let's say 1011001. Let's say this is our data. It can be much longer, of course. This could be 1,000-byte frame. I'll just take a few bits. But this, what happens on those few bits, exactly what happens on all the entire frame. And the other thing we need to agree with the other side is the generator. Generator is a number, but we'll always look at it in binary. And let's say the generator, for example, 7. So in binary, it's 111. It could be any number. There are conditions for it. We'll talk about them later. Now, it's almost the same algorithm done by the sender and the receiver with one minute difference. And you need to notice the difference or you might get the wrong results. So how does it work? I'm going to write the steps here. There are 4 steps if you are a sender and 4 steps if you are a receiver. It only has 3 steps. You skip one of the steps. The problem with Siemens, sometimes you don't skip it and you end up getting wrong results. I just want you to be careful. First one is not even a step. It's just I make sure you know you have your data and this is called the generator. This is the number or the key that will generate the remainder that we will send with the frame. So just identify, make sure you're happy, you recognize your data and generator, which is, in our case, it's clear. Here's the frame and here's your generator. You're given the data and you're given the number. Now, next thing. This is the step done by the sender. Append 0. You need to append to the data zeros. This is redundant data. You only append it at the end of the frame. How many zeros do we append? It's 1 0 less than the length of the generator. Generator, how many bits is the generator? Did you say 2? 3, right? So we have 3 bits. Then we need to append a number of zeros, one less than the length of the generator. That means in this case, we're going to append 2 zeros. So we're going to end up adding 2 zeros temporarily now to the data. And in fact, that's what the size of the remainder that we'll be sending is going to be 2 bits. But we start with 2 zeros and we see what form they take. So that's the second. If our generator is 11 bits, then we have to add 10 zeros at the end of the data. Right? It's always 1 0 less than the length of the generator. Now, start the operation, divide. Start the division. And it's not division, just remember that it's XORing. We'll just say divide, but in fact, it's an XOR operation. And just to remind you, here's the XOR table. I'll put the XOR table here. So, let's start the division. It's a long division. I don't know if you remember it. Maybe you learned it when you were a kid. That you divide, you must have a number here. You must have the same number of bits to divide that number by this number. This number always has to be the same length or shorter than. You can't divide. If you only had 2 bits, you can't divide them. That means you finished. You finished the division operation. You must always start with the same number of bits. So this one's 3. That means we're going to use the first 3 bits. Or 1. We don't care about the result. We care about the remainder. So you don't even have to write here 1 or 0. In fact, it will always be 1 in our case. And then we usually multiply that number by this, so we end up putting that number there, 1, 1, 1, underneath the data on the left. And minus that. But instead of subtracting, that's where we do the XORing. So 1 XORed with 1. 0. Yeah, see? 1 XORed with 1, it's 0. The next one is 0 XORed with 1. 1. Thank you. And 1 XORed with 1, 0. Now, the zeros on the left, we don't need them. My advice, what I do, is cross them out. They always end up causing you problems. By mistake, you start including them into the operation or into the division. So as long as you don't, if you don't use them, that's fine. But in my case, I find I better just cross it over. We no longer have that 0. Now, I can see I have 2 bits. How many bits do I need to continue the operation? The generator is 3. If the generator was 7, I need to bring down more bits to have that number. So now we need 1 bit. I'm going to bring that one down. It's good to either cross that one or have an arrow pointing from it, just in case you bring it twice later on, you get mixed up. When you see one, you go to the next one, especially if there's few ones or few zeros. Anyway, so I bring 1, 0, 1. Now I have 1, 0, 1. That divided by that, whatever it is, we bring down the 1, 1, 1 again. 1, 1, 1, and we do the XOR. 0, 1, 0. That friend in the corner there. What result is this? 1 XORed with 1. 0. 0, and then 0 with 1 is 1, and that's a 0. And then I'm going to cross that 0 on the left. Now, I'm going to bring again, I need 1 more bit. So I bring a 0. And that we divide it by that, we're going to bring the 1. Oh, that's all you have to do is just bring in that generator here and XOR it with this. So you're going along the frame. You keep going all the way to the end. That's why they call this CRC the cyclic. Cyclic, I mean, you keep cycling along the data until you reach the end of the frame. Redundancy check. That's what C stands for. Cyclic redundancy check. Right, so now we have another one. Who's gonna help me here? Yeah?
0, 1, 1.
0, 1, 1. Thank you. Right. How many bits will I bring down?
One.
1 bit. So there it is. And I bring down the 1, 1, 1 here again. And what's the result here? I have a volunteer, yeah?
1.
1,
0, 0, 1.
0, 0, 1. That's better. Okay. Now, how many bits do I need to bring down?
2.
2 more. So I bring down the 1 and the 0. And continue. And that's 1, 1, 1. And that's okay.
0, 1, 1.
0, 0, 1.
Where is 0?
Are you testing me or what? Yeah. You get rid of the 2 zeros on the left. Sorry, I didn't. And how many bits do I need to bring down? We need to bring 2, but we don't have 2. We only have 1. And we have to stop because that's it. We've finished. We cannot continue. If we don't have as many bits as the generator, then that means we've reached the end. And that's the remainder we have. See now, whatever, if you look at the digital value or the decimal value of this number and divide it by the decimal value of this number, which I know it's 7, I don't know what that decimal value, if you divide them, they'll actually have a remainder. And that remainder is 1, 0 in binary, which is 2 in whatever it is. And it's also the complement. That's a good thing about binary. That number is the remainder, but it's also the complement. If the 1 complements 0, the 0 complements 1. So it's a lot quicker and easier, but we don't have to work out, hey, we got the remainder, what's the complement to that? In binary, it's already there. And when you have that left out there, that's where it goes at the very end of the frame. Right, I just didn't put the last step here in the center. What did we do? What's the last thing we did? We first identified our data and our generator. We appended zeros, and here are the 2 zeros. And then step 3, we started the division or the XORing. We should say, take the remainder, append, and that will be your frame. So just append to data, to the data. And how many bits do you append? Same. Length of the generator minus 1. So that's why here we had 1, 0. But even if we had 0, 1, we don't just append 1. We have to append it with 0. So these are the steps that are followed by the sender. So now what's the data? That's what we send at the end of that frame. And that's the actual complement, or the remainder. And that's also called the CRC. And that's called and it goes into the frame check sequence, they call it. So now we take the full data without the 0, 0. So now what data shall we send? That's the last thing you need to say. Okay, that data we're sending is 1, 0, 1, 1, 0, 0, 1. That's the original data. And now we have to send as many bits from the remainder as 2 bits. That's 1 less than the generator. Just for argument's sake, if the remainder was, just imagine if it was, it is not now, but if it was 0, 0, 0, 1, if that's the remainder, and then you'd have crossed all these. How many bits will you add in here as a remainder? You must add 2 bits because it's 1 less than the generator. You only have 1 when you insert a 0 on the left-hand side, right? So pad it with zeros if you have to.
Left or right?
No, on the left. The right will change the number completely, but you have to pad it on the left. So, but in this case, we just have the perfect number, 1, 0. But if you only had a 1, you must pad it with. For example, if our generator was 11 bits, and you had here 1, 1, the remainder, but then you must put 9 zeros behind, or 8 zeros. Okay, so remember, you must take from the remainder as many bits as there's a number of zeros you put there, or as many as 1 less than the generator. If you don't have enough bits, pad it with zeros on the left. Now, so that's what we end up sending. You need to know now, as a CRC, if you knew the generator had 3 bits this frame is the data, and which part is the redundant data, the extra, the CRC, the one that's not part of the user. You say, okay, our generator is 3. That means the extra redundant data means 2 or 1 bit less than the length. So that means only 2 on the left. The rest of it is all user. So now you know this is the user data, and this is what we call the CRC, or the redundant data that goes with the frame. Yeah.
Why we should remove last 2 zeros?
Remove the last what?
Last 2 zeros.
No, we put those just temporary for calculations, but in fact, this is like, it's like you take those numbers, like in parity system, where it starts. Remember, in parity, we say you count how many ones. You don't actually count. Computers maybe are not great at counting, but they're great at ending. Takes the first bit, and do the second, gets the result, add with the next, until the 7th bit finished. They're left with 1 or 0, it leaves it there. So it's really, really fast. This one is pretty much the same. It just looks complicated to us, but computers are so good XORing, they just keep, at the end they're left with 0, and the data is gone. And in fact, it's so fast, faster than any other system because of another advantage. The first reason is that it's a logical operation. It's XOR. Computers are so fast at logical operations. ANDing, ORing, shifting, XORing, these are all comparing two things. They're not good at adding and subtracting and multiplying. They're really, really slow, well, in relation to other operations, of course. The other reason that makes this CRC algorithm so fast is that when you have the whole frame, in most other systems, you must wait until you finish all the operation and put the CRC or put the additional data and start sending. CRC says, no, where's the start of the frame? That's the start of the frame. It starts working and just goes few bytes into the frame, and it says to the physical layer, you can start sending the frame. So the transmitter is sending, and CRC is running ahead of it. And the sender is sending, the transmitter is sending. By the time it reaches the end, it leaves the remainder in its place, and the transmitter sends it. So you don't even have to wait until it finishes the work. First, it's so fast, but also there's no requirement for the sender to wait until the work is done, and then you say you can start transmitting. It just starts immediately before the transmitter starts and starts going through it, flying through it.
Sorry.
So the speed is probably the fastest system available today.
But in that case, if we say no, a number that we are sending error,
Right now there are no errors. The errors can happen during transmission. Now we have the data. We're starting. We're going to send the data. We're not checking for errors. We are. I done it earlier on. You divide and you find what would complement this number to make it divide by the generator without any remainder, and that's what it takes. That's what's left is actually the complement.
Also, wondering this number 111.
It's 111 in binary. That's number 7. Yeah.
In binary.
Okay.
Where it comes from? How we found it?
Okay. We'll come to that. Right. This is agreed by the sender and generator, by the sender and the receiver, and this number is actually depends on the network. The network doesn't change it. You join a network, they say to you, here's our generator for CRC error detection system. You put it in your program and that's it. It's one of the inputs you take and never change, or maybe rarely change. And then the whole network needs to change it. And also many, like back in the 70s, they've done a lot of research on this system, and they came up with the best generators, the ones that will give you the performance possible, discover more errors. And there are about 4 numbers maybe altogether that the scientists came up with. And they put it in the regulations and standards that were issued. So there's an actual standard and say, okay, here are the 4 good numbers, best numbers we found. So your network will just pick one of them and everybody knows it's not a secretive number. Right? Very fast. Now, that's why we send, let's see how it works. How does the receiver really, what does the receiver do? And something similar operation. Right, you'll need to be able to do this calculation. We'll have a quick example after we do see what the receiver, how does the receiver work. So let's say we've just sent this frame. I'm going to write the same frame. It's 1 0 1 0 0 1 1 0 1. That's the received frame, and our generator is 1 1 1. Now we're acting as the receiver. Let's see what's the steps that are followed by the generator. They're pretty much the same. Identify your data and your generator, and in this case your CRC as well. Don't append 0. That's the only difference. Don't append 0. If you get a question in an exam, read the question carefully. Are you a sender or are you a receiver? If you're a sender, you're going to append zeros. That's the difference. If you're a receiver, make sure you don't append 0. Every year I put similar question, and out of the group I get 4 or 5 students who appended zeros in the case of a receiver. And of course they give you. Be careful. Okay, let's see. First step is the same. Identify, but this time you have to identify one more thing. Identify your data, your generator, and your CRC. Now we got this frame. Okay, the generator, we all know what they'll be agreed. Now we have a frame that has data and CRC. Right, so what's the second step? We should go straight into division. But what I'm going to do first, do not append zeros. So you remember it. Remember, we are receivers now. It's so important that I write it, don't do it. Because some people actually do it, right? So the next step is the same. And divide, or it's not a real division. What is it? XOR. XORing. Right, so let's divide. So Rahman, please. I'm going to put the 1 1 1 and you tell me what the result is. Quick.
0 1 0.
Right. Across this 0, I'll bring down 1. Right, I'll put 1 1 1. Keep going.
0 1 0.
0. Guys, follow me, because if I make a mistake, then 0 1 1. Bring down a 0. 1 0 0 1. How many bits will I bring down? 2 bits. That's 1 and that 1. And bring down the 1 1 1, and they're all zeros. Bring down the next 0, and that's it. We're finished. And the remainder is 0.
Not to append 0.
Pardon?
In the second step, do not append 0.
Yeah. Don't add zeros to the end of your data. Don't put more zeros like we did as a sender. When you were a sender, zeros of 3 zeros of 5 at the end of the data. If you're a receiver, don't do it. Because there's already, remember guys, when I say first identify your generator. Here's the generator. Identify data. Where's the data? The data is all the way to there. That's the data, and that's the generator. How do I know this is the data? How does the receiver know that's the data? That extra 1, that last 1 is not part of the data, or maybe this 0 is part of the data. How does the receiver know?
CRC is 1 less than the length of the generator.
Because the CRC at the end is 1 less than the generator. You look at your generator. If this generator has 3 bits, that means the last 2 bits are not data. If the generator was 10, then the last 9 bits are not data, and so on. Now, the last step. Just look at the results. If the remainder that you get is not 0, what does it mean? It means there is an error in the frame. If we get remainder 101 or 001 or any one in it. If it's not 0, then there is an error. If it's 0, what does it mean?
No error.
No error. Okay, most likely no error because there is a probability of 0.0001 possibility that error that CRC cannot discover. Even CRC cannot discover 100% of the errors, but it discovers them to 99.999 of, accuracy. So you get to ask the question, you do it, answer it, and at the end you say, the remainder is 0, that means no error, you don't get 10 out of 10. This last statement is important to say something to the effect, most likely, probably, or most likely, no error. Or error-free, or whatever you want to say. But you can't say error-free, it's free of errors. You cannot say that. Not 100%. Okay? Can we try it out with just flipping one of the bits, right? So imagine when the sender sent us the same information, I'm going to write it down again so I don't make a mistake again. 1, 0, 1, 1. This is the received packet or frame. 1, 1, 0. That's what we received. And that's the actual data, right? The generator. Now, I'm going to rules. But I want you to look away for a second. I'm going to flip one of the bits, right? Which bit? We're changing one of the bits. Let's see if CRC will discover it or not. Right, so let's follow this is what we received. This is the frame we received. We know this is the data. And the last thing when you do as a receiver, you have to separate the data from your CRC and throw away the CRC. As you can see, guys, the amount of redundant data that we send is quite, it happens at the very end of the frame. In fact, the standard is 2 bytes for every frame. Like a frame is 1,000 bytes or 2,000 bytes, only 1 byte goes at the end. So it's a ratio of 1 to 1,000 or even 1 to 10,000, in redundant data. So redundant data is very, very, very small compared to parity systems. So this is as good as parity system in speed because it's a logical operation. It's better than parity system in redundancy. It's 1,000 times better, maybe, because you only send 2 or 3 bytes at the end of any frame or packet. 1 byte. I think the standard is 2 bytes. Okay. And when you finish as a receiver, then you must say, okay, guys, I'm gonna separate those 2. And once you're happy and the remainder is 0, then you should say, okay, here's our user data. That's 10101. That's the data received. You have to get rid of the last 1 and 0 because they're not data. But once everything is received correctly. Now, let's imagine this is the receiver again. We receive this frame. And this is the kind of question you get. You're after receiving this frame, that this generator was used. Does it contain an error? Now, you are a receiver at the network end. You've received a frame and you want to check it. This happens at every router. Or at the final destination. Every packet or frame is error checked. Right, so let's do it. First, identify your data. Here's the data. Your generator, here's the generator. And CRC, that we know the last 2 bits are CRC. These are the ones we throw away if everything goes well. Do not append zeros. So because we already have CRC, we don't need to append anything. As a receiver, we don't append. Divide or do XOR. So I'm going to start the division or XOR. Okay, who's going to help me? Yeah, okay. So I'm going to start placing 1, 1, 1.
0, 1, 1.
0, 1, 1, thank you. Cross the zeros, and then, should I bring one down from here?
Yes.
Yeah, so that's the one came down and put 1, 1, 1, and
0, 0, 0.
are you sure? Okay, keep going. Will I bring 3 bits? That's a 0, that's a 0, and that's a 1. Right, is that okay? No.
No. 2 more bits.
Zeros on the left are no good. Keep bringing down bits until you have 3 bits. Let's start with a 1. Okay, guys? You can to 0 and you multiply 0 by 1, 1, 1, you end up putting zeros here and you keep it just longer, more complicated operation. So keep bringing down as many bits until you have, now we have zeros on the left are no good. You bring 0, yeah? And then we put 1, 1, 1.
0, 0, 1.
0, 0, 1. We're finished. We have nothing else to do. Data is finished, CRC is finished. The remainder is not 0. What does that mean? Not 0, that means it's definite error. See, if the remainder is not 0, definitely we can, happily and confidently say there is an error, 100%. If the remainder was 0, don't be so definite about it. But see, as you can see, we discovered that there is a bit. So this system works pretty well. And of course, the bigger the generator, the more likely that it will work even better. And there are some generators that work better than others. Now, everybody's okay with that? Good. Now you're a sender, guys. You are a sender. Here are the steps for a sender, and I'm just after doing this. I'd like you to do this. I have 4 minutes maybe to do this. Here's your generator, and here's your data. Please produce the frame that we need to send. Produce the CRC. As a sender, you have 4 minutes. If you don't know how to do it, put your hand up. How to start, if you don't know how to start. Here are the steps. Identify your data. Here's your generator. That's generator. Append zeros. Don't forget the zeros.
How can I know how many zeros I should?
Yeah, how many zeros? How many zeros you append? Append zeros. 1 less than the length of the generator. Where's the generator? There. How many bits does it have? 3. 1 less than that. Always look at the generator. Go on, start away, guys. Who doesn't have a piece of paper? Piece of paper, go on. You have a pen? Yeah. A pen. I don't know if I have a pen. Let me check. Will a red pen do? Red pen? Okay, good. Anybody else? Are you nearly finished? Yeah. Right, okay, good. I'm gonna go through it very quick. You have done it? If you haven't done it, this is the way it should be done. Yeah, I'm gonna start the division. Guys, I've identified this, and that's my data. Append zeros. Did you append zeros?
Yeah.
How many zeros?
2.
2 zeros. Why 2 zeros? Because the generator is 3. You have to only 2. Right, so these 2 zeros are not really part of the data, or they're not part of nothing, but they're just important for the operation. Divide or do XOR. So I'm gonna put down here 1, 0, 1.
0, 1, 0.
0, 1, 0. What's next?
And we can take one.
Bring down the 1 from here, so that's 1 of 1. Put down the next 1, 0, 1, and
0, 0, 0.
3 zeros, gone. Bring down 3 bits.
No, 4 bits.
We'll bring down 0, it's no good. Bring down 1, 1, and 0.
1,
0, 1, 1.
0, 1, 1. Get rid of the 0 on the left, bring down the next 0. It's quite good to watch or cross out or point the rid of or you use, so you won't end up using it again. 1, 0, 1 and it's 0, 1, 1. Bring down the last 0 and it's 1, 0, 1 and it's end up 0, 1, 1. This is the remainder and it's also the complement. So now the rest of your answer should be, this is the data we take, that's the frame 1, 1, 1, 1, 0, 1, 1, 0. Don't take those two zeros and append to them two of those bits starting from the right hand side. So it's 1, 1. So now that's what we end up sending. This is the frame that includes the CRC. And in most packets or frames, they call it the frame check sequence. Some people gave it a name like that. Some networks call it the frame check sequence. Call it the CRC. It's the extra redundant data that gets sent, generated and sent by the sender in CRC system. All right. I'm gonna this is your generator.
It is 1 bit extra.
Is it again sender?
This is another example. You're a receiver now. Please tell me, does this data, okay, I'm gonna add one more one. Does this have an error or not? You've just received this frame. The sender used this generator. Frame received correctly or it has an error. It's the last work you have to do today. You can relax. If you get this right, you're laughing. You're gonna be happy. Should have 10 zeros here. Maybe that's why excuse me. The businessman. Right, okay. Guys, don't forget here, you're a receiver. You identify your data in your generator. Do not append zeros. Some people didn't. And check the remainder. This is our generator of data, and the last 3 bits are our CRC sent to us by the sender. So if we're happy and there's no error, we throw away the last 3 bits. Not append zeros and start the division. I'm going to start dividing. Right. You read out the results, right? Let me write the 1, 0, 1, 1 all the time. I'm good at writing that. Right, you read me now.
0, 0, 1, 0.
Good. How many will I bring down?
2.
1 and a 0.
Yeah.
So it's 1, 0, 1, 1.
Yeah. 0, 0, 0, 1.
Good. So we broke those two. We're going to bring the next 3 bits. So it's 1, 0, 1. Are we going right here?
Yes. 0, 1, 1, 0. 1
I'm almost going. That's it, the end of operation. We have remainder 1, 1, 0. Do we add that 1, 1, 0 to the data? Receivers, it says, is the remainder 0 or not 0? In this case, it equals 0. It does not equal 0. That means remainder does not equal 0, which means definite error. Oh no, you just throw away the entire frame or packet. So well done to those who said, yes, there is an error. Actually, some people fooled me already and said, there's no error. Okay, so that's CRC. This is probably the most used system in computer networks. But remember, parity is older and it's been in use for longer. And it's not just in communication networks. Every time you store your files on a hard disk, they're parity checked and extra parity bits are stored. And every time you read it, every time you send a file to the printer, it's already built into all those old programs for parity. I'll probably tell you, no, there's something wrong with that. We won't print it. But which one is better now? Parity systems or CRC systems? That was the question that we started earlier on this morning. Which one is better? CRC or parity? CRC. CRC, that's a good answer, but it's the wrong answer. As far as speed is concerned, maybe we don't care too much about the data, even if it has errors. Some data doesn't matter if there's error or not. Maybe then whatever is there, but out of general, I think CRC, except for speed, it has the same speed as parity, but everything else, it's a lot better. The number of errors detected and the redundant data is a lot less, far less than parity system. Now, there are some errors that cannot be discovered by CRC. CRC will not discover the following errors. It will discover, okay, odd bits with error. So if you have 1, 13, 15 in the full frame, not in each byte, in the entire frame. Any odd number will be discovered 100%. What about we will discover all odd bits, all frames, odd or even, under the length of the generator. What if they are even? Well, if they are under the length of the generator, they'll be 100%. And at the same time, more than the length of the generator, then they'll be discovered at the rate of 99.9%. So it has a very high discovery rate as compared to the parity system. As well as this, the other point I want you just to know is that given to you in binary format, unfortunately, or fortunately. The people who wrote the standards, yeah.
What is the meaning of even and?
Even, that means 2 or 4 or 6 or 8 divided by 0, and at the same time, the number of errors is greater than, and this is logical and. So, okay. So bigger than no, we're not talking about 2 or 4 bits or 6 bits, we're talking about 26, 28, 30, and so on. If they were less than the generator, they'd be discovered anyway, odd or even. Now, let me very briefly, I just want to mention, anytime you're given a standard, the people who wrote this CRC standard, the international standard that's being used by almost all networks, they also found good generators. People have done a lot of studies to find some generators will work better than others. And usually the generators are either 2 bytes or 3 bytes. They're standard in networks. So with every frame, you're sending 2 bytes at the very end of every frame or packet, or 3 bytes. So that's the amount of redundancy we're using. With packets, like it can be 3,000 to 4,000 bytes a packet, maybe longer, even bigger. Format, what does it look like? When you are sent the number, it's going to be written like this: x, for example, to the power of 6 plus x to the power of 5 plus x squared plus 1. That's how they write it. They don't give you 100110. And the point is, they said, okay, because for long ones there'd be lots of zeros. Sometimes there'd be 6 zeros. You think there are 7 or 5. You make mistakes, so they don't do it that way. So they think this is an easier way. Okay, but so it's up to you to convert this number into binary to use on your computer, your exam, whichever the case is. So the way they do it, they only give you the ones. You have to make up the zeros, right? So these X's here represent the position of the ones in the generator. You need to fill in the zero. Just one other condition. Every generator must start with 1, cannot start with 0 on the left, and must end with 1. So this is a thing for you to know, or it's a condition, one of the conditions for the generator. It starts with 1 and ends with 1. So, for example, in this system, this is 1, this is the last one, and that's the last one on either side. Now you have to fill in what's in between 1s and 0. So they give you the 1s and start walking down from here, this way, starts with x to the power of 6, that's translated into 1. If it's written there, replace it with 1. Then after 6 we have 5, that's there, so we replace it with 1. After 5 we have 4, 4 is not there, so we write a 0. And then after 4 it's 3, it's not there, to the power of 3 is not there, then it's a 0. Then there's the power of 2, it's there, it's 1. Then we have x to the power of 1, it's not there. And then finally, that one there represents actually x to the power of 0. Anything to the power of 0 is the value 1. So that's the polynomial format. This is the binary format. And you understand it? So they only tell you the ones. You have to insert the zeros at the right place. Let me give you one more example, and then I'm going to ask you a question. Right. Here's another generator. Give it to me like this. X to the power 5 plus 1. Can you help me with this?
0, 0, 0, 0, 0, 0, 1.
I think I'll probably stop at this. Okay, the 5 here, 1. This is x to the power of 4. This is x to the power of 3, x to the power of 2, x to the power of 1, and finally x to the power of 4. X to the power of 5 plus 1 is 1, 0, 0, 0, 0, 1. That's the equivalent. Right? I can see you're nodding with your head. So maybe you can help me with this. X to the power of 7 plus x to the power of 3 plus 1. Can you convert this into binary, please? Yes? 1, 0, 0. Okay, no problem. Good. So let's. Okay, right? Make sure you know how to convert it. Because that's what you get in an exam. You're told this is the data, the frame you received, and here's the generator used. And the generator will be in polynomial format. First thing, you have to convert the polynomial format into binary, and then work away. You make the wrong conversion, your results are not going to be correct. Let's go to the next. What time is it, guys? Well, it's called Hamming code.
Next thing.
The last one, there's another one, but we haven't. Let's skip it for now. Hamming code. Hamming code is not just an error detection system. So far, we've looked at 3. There's one more system we haven't looked at. Error detection systems. Hamming code is error detection and correction system. So it tells you there is an error in the frame, and that's the bit. Change it. If it's 1, turn it 0, or if it's 0, turn it 1. The only way to fix these errors using the other system, CRC, how do we fix an error in a frame? If CRC discovers, tells you this frame has an error, how do we fix it? If you receive a frame with a problem, CRC tells you there's an error. How is that error fixed?
Change the.
Resend the entire page.
Retransmit. The only way to fix it is to ask the sender to resend the frame again. But now we're looking at having code where, hey, you don't have to send it. I know which bit number 26, so I don't change it. If it's 1, turn it 0. If it's 0, turn it 1. And here's the data correct. Right. Now, how does this? It works. It's based on parity systems, but it works in a nice way. And to do that, imagine if we split our data into areas and we see where they intersect. Data 1, 0, 1, 1. And let's write the first bit 1 here, the 0 there, the other one is here, and the last one there. So this is bit 1, 2, 3, 4. This is the location 1, 2, 3, 4. So we take a frame, or whatever it is, the data we have, and we split it into separate areas that they intersect on different bits, as we can see here. See now, imagine this is area A, this is area B, and area C. So area A now has 3 and 4, has that one down. Area B has bit 1, 2, and 4, 1, 2, and 4. As you can see, every area, every bit may be a member of 1 or 2 areas, or even 3 areas. This is where the parity comes in. And this is what Hamming code did, the idea. This is the idea. He said, okay, look now at each individual area, or circle in this case. And let's do a parity on this circle. And let's, for example, are we going to be using odd or even parity? I'll give you the choice. What would you choose, odd or even parity? Even it is. Good, thank you. All right, now, but I'll give you the option now to tell me what parity will go in area A to keep everything even. This is area A, it has 1, 2, 3 bits. That's an odd number. So the extra bit that we're gonna add, shall we add a 1 or a 0 to make it even? We add 1, so now we have 4. In area A, we have 4 ones, that's an even number. Now, area B. Hey, the lady with the cake. Area B, do we add a 1 or a 0 as a parity to make it an even number? 0, thank you. That makes the MB has 2 bits that have the value 1. That's an even number. Area C, 0. A 0. So that's how Hamming code system works. So just do that, and you discover any error, and you know exactly which one it is. Now, I'm gonna flip one of the bits. I don't want you to look, just look away for a second. Just flipped one of the bits. We don't know which one. Now the receiver. Imagine now we are receivers. You receive this data. Where is the error? You go to area A, you count it. You should have an even number, 1, 2, 3. So we say area A has a problem. We don't know which one, because it could be 3 of those bits. Which one of them has the problem? Now let's go to area B. Area B, we count, it has 2. Does it have a problem? No, it's an even number, so it's no problem. Let's go to area C. You count, there's an odd number, there's an error. So now we know there's a problem with area A and area C, but no problem with B. So which bits intersect, A and C intersect in, and they do not form part of area C, B. So area A and B They share those 2 bits, the 0 and the 1. But that one is part of B, and B has no problem, so it must not be in the system. So that leaves us with this bit here, and that defines which bit. And this is the bit I switched off without you know. Okay, do you understand how it works? No? Who said yes? You understand how it works? You know how it works? Yes? Okay, then tell me this. I'm gonna change another bit. Look away for a second. Right. Now, tell me, where is the bit with the error? You just received this now. I put this one back to 1, so it should be 1. But now, the rest of the bits, where's the error? And how do you know? You check area A. Does it have a problem? Yes, so we have a problem with area A. And area B has a problem, right? And area C? So where is the bit that intersects? A intersects with B, intersects with C. They all intersect in 1 bit. The one in the middle. So you know immediately that 0 should be a 1. You just fix it and that's it. That's all the problem. Now, this is the basic idea. This is the general idea of Hamming code. Now, all we have to do is smooth it back, open them up, back into this frame, and put also the parity bits somewhere. Maybe we put the one here, the second parity bit. Remember, this is the same data we have, except the parity bits. Maybe we put this parity bit here, maybe that one there. Just now, where to put the parity bits in the data, and we know which ones form which group. And there's an easy, a quick and simple way. So that's what we're going to do now. We're going to have an example of how Hamming code can be used. Where do the parity bits go, and where do the data bits go? And if one of them flips, how to actually find out which one it is. It's very simple and a quick way, and it uses the old parity system. It's extremely fast. So, you know, you have the overall idea. We split our data into groups, and every group has its own parity bit, but these groups intersect, and through that intersection, we can tell which bit has formed the error. Right, I'm gonna give the actual slides because, you know, it's easier to, instead of redrawing the whole thing or writing, so let's switch off to the, I think possibly this week. If we cover the material, we should finish error detection. I don't want to spend too much time as well. I also expect that you should know all this stuff, well, most of this stuff anyway, but it's good to go over it. And right, let's go straight to Hamming code. We can read the material, but let's go straight onto an example.
It's not visible on the.
Just testing you again. All right. This is how Hamming code is implemented on data, on frames and packets. In this example, we're going to have a few parity bits in our data or in our frame or packet, and some data bits. Guys, I can hear buzzing going on in the background. Makes me, and that doesn't work. Right. What we are looking at the moment is 12 places in a frame that has 12 bits. But we're not really sending 12 bits, we only have 8 data bits. So we're going to send 8 pieces of data in bits. But this goes, you know, for much bigger frames as well. And some of the positions are defined as the parity places, parity bits. So we don't put data in the parity locations. Locations are defined by the powers of 2. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 4, and so on. So it doesn't matter how big the frame is, bit number 1 is parity. Don't put information, don't put your data there. So 2 to the power of 1 is 2. So location 1 and 2, they belong to those 4 parity bits that we had earlier on. Parity bit 1, 2, and 3. So 1, 2, just 32, 64, these are all parity bit locations. Don't put your information in. So that's the first thing you know. The rest of it, just take your data and fill it into the rest of the available frame. So if we get, say, 5 bits or 10 or so, the first bit goes here, the next bit there, in location 3, 5, 6, 7. Don't put nothing in 8 and so on. All right, so that's how it's done. So now let's get an example. So there are 2 ways to numbering this. I only go by bit of numbering, the exact location of each bit, right? Starting from number 1 as being the first one. Some other numbering schemes, they go by, okay, that's parity bit number 1, parity 2. This is parity bit location 4, parity bit location 8. And the data goes here, data 1 goes there, data 2, it's okay as well. But once you understand where the data goes, you don't really need those. As long as you don't put data in location 1, 2, 4, 8, 16, these are booked for the error detection parities. So if we get a frame to send, here's the data. Where would I locate the first one here? What position would the first one bit go? It goes into position 3. See, that's where the first thing. You can't put data in parity locations. So here is where we put the bits. Excuse me. So the data, excuse me. There you have to get off my throat. In the frame, in the correct locations. Now, all we have to do is start filling in the parity value for each group. Now, how do we know which group goes with parity 1? Now, here's the system. Every parity bit is known by its number. This is parity 1, its location as well. Parity 2 is in location 2. Parity 4, we don't say this is the 3rd parity bit, we call it parity 4, even though it's the 3rd parity bit, but its location is in location 4. It's easier to know that way. And parity 8, it stays in location 8. But the good thing about it, something that you'll need to remember, starting with the parity, let's say 1, start with 1. If we are working on parity 4, we start at location 4. Right? So you start at the parity number. If it's 1, start at 1. Skip 1 each time. So now, the group that are associated with parity 1 are all the numbers that starting at 1 include number 1, and then skip 1, skip number 2, 3, skip 4, 5, 7, 9, and keep going until you reach the end of the frame. So this is the first group. Remember the 3 circles we had, A, B, and C. A includes those bits. So parity 1 is associated with all the bits starting from 1 and then skip 1. Parity 2 start with 2 and skip 2. Now let me just go a little bit further here. This is how what bits are associated with parity 2. You might want to remember it this way. You might have another way to remember it. Starting at number 2, take 2 and skip 2. Take 2 and skip 2, take 2 until you reach the end of the frame. What about parity 4? Where do you start?
4.
And how many do you take? 4. And skip 4. So let's see it again. This is number 4, if we go to number 4. You start at number 4, you take 4, 4, 5, 6, and 7, and then skip 4, 1, 2, 3, 4, and go to the next one, take the next 4. Parity 1, you take 1, you skip 1. You take one, you skip one, and you start in at one. Maybe if you remember those three words, where do you start? How many do you select? How many do you take? And how many do you skip? That's at number one. How many do you skip? You skip one. You go take the next one. Skip one and so on. If it's two, the other way around. So let's take it now. Go back. It's how we started. This is as a sender. You take the data, put it in the correct locations. Don't use the parity locations. Now, all we have to do now is decide what value shall we put in parity one, a 1 or a 0. In order to know that, first you need to know what bits there are and see even or odd. I don't know. Doesn't even say. Let's say we go for even. Now, this is how it works. Then I'll work out what value this one is. First, we start at 1, skip 1, we look at number 3, we skip 4, we look 5, so 3, 5, 7, 9, 11. If we take them out, but you can count them on the spot, but just to make it easier now, if we take these values out and we don't know what parity 1 is. So we count 1, 2, 3. We want even. That's an odd number. So that parity 1, let's put a 1 to make this group an even number. There it is. We put 1 in there. So we finish now with parity 1. Let's go now to parity 2. Parity 2, we're going to have another group. Start at 2, pick 2, skip 2, look at another 2, and then see if they're odd or even. So here's parity number 2. We start at 2, we take 2 and 3. We take those 2. Skip 2, that's 4 and 5. We go to 6 and 7. Here they are, 0, 0. And then we skip 8 and 9, we take 10 and 11. So that's what we have, including parity 2. We have the ones that are only 2 ones. That's even. That means the extra parity. Shall we add a 1 or a 0 there?
0.
0 to keep it even. Understand? Good. So let's go now to parity 4. You start at 4, you take 4 bits, and then skip 4 and take the next 4. Skip 4, take the next 4. Here we go, we take the first 4, 4, 5, 6, and 7. We put them down here. We don't know yet. 1, 0, 0, here they are. And then we skip the next 4, 8, 9, 10, 11. And we take the next 4, that's number 12 onward. There's nothing else, so we just take that here. And we look at this. How many ones are there? It's the odd number, so we add a 1. So now pit 4 becomes 1. Okay, what do you think? What value should go into parity 8 before we go to 8? Start at this location, take 8 bits and make sure there's an even number of 1. You want to work it out? Anybody wants to work it out? Did you put your hand up?
Can it be 1?
Does it? In 8? Yeah, we start at 8. In 8 here, we start at this number 8 and we take the next 8 bits. There's only 1, 2, 3, 4, 5 bits altogether, including 8. And there's only 1 odd, so we add a 1 to make it even. So number 8 should be an even number. See, the way you pick it, you start for parity bit 8. You start at number 8, take 8. So you take 8, 9, 10, 11, 12, there's no more. That's it, you stop there. How many ones does it have? It only has 1 bit that has the value of. That's an odd number. Then make the parity bit a 1, make it even. And here's now the frame that goes out. So we're after filling all the parities for this frame. Usually I give another example in this particular way. So let's go this way. Here's 1, 2, 3, 4, 5, 6, 7. How many? 7 will do. 7 and 3 is 10. 8, 9.
We cannot see, so on that.
Let me give another example just to make sure we're okay with that. Right, here's an example. We're a sender. You want to send the data. First thing, you're going to work out, let me number the data. So first, we're going to put the location 1, 2, 3, 4, 5, 6, 7, so on, 10. Now keep going. First bit goes in here because remember, what are the locations that are parity?
2 to the power.
What locations are reserved for the parity bits in a frame? Here's a frame that has all these locations. Which of them are the parity bits and which of them should be data bit? Okay, this is a parity bit. That's parity 1, parity 2, all the power of 2, 1, 2, 4, 8. Position 4 and position 8. And you keep going. Maybe position 16 if the data is bigger. Don't put any data in those positions. So where am I going to put the data? That first one goes in there. That next one goes there. Sorry, not there. Thank you. I was just checking. And then the next one is 0, goes in there. And then 8, and then 1 and 0. That's location 11 and 12. So that's where the data goes. Now I want to work out what's P1. It's the way I expect to go about it. So right, P1 guys. Bits. Which bits are associated with parity 1? Can you tell me which bits? With parity 1. You start at 1. And you take it, skip 1, take the next one, take 1, skip 1, take 1. So tell me which bits, which locations. Location 1.
Sir, I think we did a mistake, but I'm not sure. Should the 9 was 0 or 1?
The last are 0 from the right, 1, 1, 1, and then 0, 0. Yeah, you're right.
9 should
So that's
be
1,
0.
1, 0, 1, 0. That should be a 0. Okay. Shall we change it or shall we get rid of the one up the top? Which one is easier? Okay, we'll change it. We'll stick to this example. So number 3 ones and location 13 is a 0. Okay. Is this correct?
Yeah.
Thank you. Okay. Guys, the way to do it. Parity 1. We'll take 1 and 3, 5, 7, 9, 11, 13. So what value is 1? We don't know. What value is 3? It's 1. 5 is 1. 7. It's in fact, it's better to have a table so you don't mess them. You know? And stay right on the and 9, 11 is 1, and 13 is 0. Right? These are the bits associated with parity 1. It's location 1, 3, 5, 7, 8, 9, and so on. No 8. You start at 1, take 1, skip 1. Keep taking 1 and skip 1. How many? 3, 4. That's all. Let's say we want even. The sender parity system. So therefore, so P1, so this is already even, so P1 should be a 0. Oh, yeah, 1, 2, 3, 4, yeah. So P1 is going to be a 0. You know why it turned out to be a 0? Because the bits that are with it are in. Now, I'm going to start with parity 2. At the back, guys, are your hands up? Are you putting your hand up? No? Okay. What bits are associated with parity 2? Please. Just tell me the number, the positions here. We start with 2, right? We don't know what's there, yeah? Yeah, no, just tell me the position so I know. 3, yeah, I put the 1. If I put the wrong one, tell me, yeah? And then, what position? 6 and 7, which, and 1. And then, you skip the next 8 and 9. 10, 11. Yep, skip 12 and 3, or 13. Now, how many bits there that have the value 1? They are odd. See, there's 1, 2, 3. We want them to be even. That means we must put this one as a 1.
There you go.
Where's the 4?
1, 3, 4. In the last.
10 and 11.
Sorry. Okay. I was just testing you again, guys. The testing is. Okay. So it's another 0. Thank you. Now, who's going to help me with parity 4? This gentleman here? Yeah? Just tell me the locations that I should take into consideration. Hurry up. Remember, that's parity 1 done. That's parity 2. Now we're working parity 4. What position shall I start with? I can't hear you. 4, okay. Right, so position 4, we don't know what value it is. What other positions shall I take?
8.
No, what do you mean 8?
5, 6, 7.
4, 5, 6, and 7. So I start at 4, take 4. So take position 5, which is 1, 6, which is 0, 7, which is 1. Now we're going to skip 4. Skip 8, 9, 10, 11. And take the next 4. There's only 4 left, 2 left. Right? Guys, you need to understand how this works. You need to be able to do it. This is another exam question. Here's the 1. Oh, so it becomes 1. So right now we have 1, 2, 3. They're odd at the moment. The data is odd. That means we need to add 1 to make it even. And this one here becomes 1. So parity 4 turns out to be a 1. Okay. What about parity 8? Give an elbow there, please. Yeah, please. Parity 8. What bits are associated with parity bit 8?
8, 9, 10.
You start at 8 and take 8. Okay. Oh, starting at 8, we don't know what. At this value we don't know, but we take 9, which is 0, 10 is 1, 11 is 1, and 13, and that's it. That's another odd, and in this case, we need to add a 1 here as well to make them even, and therefore parity 8 should be 1. Time to go?
Yes.
We act as a receiver. Now we've acted as senders. One thing before you go. Plus 1 in binary. This is a polynomial.
0, 1.
Oh, you can hardly see it. It's x to the power of 4. So this is x to the power of 4 plus x squared plus 1. What did you say? 0. 1. That is an eraser, yeah. Thank you.